This is quite a crowd. It actually quiets down before we actually are ready to start. I can't believe it. This must be a semiconductor crowd. They're used to really producing things. I'm John Toole. I'm the Executive Director and CEO of the Computer History Museum. And while we do a few last-minute things here and get ready for tonight's event, I want to tell you just a couple of things about the Computer History Museum itself. Are there many people here that are here for the first time? Wow, what a group. I hope you've had a chance to see some of our exhibits, which is really just our first phase, visible storage, the work that we did with the Intel Museum several years ago, Innovations 101, and of course the history of computer chess. Exhibition is only part of what we are, however, because we do so much more. We have a whole series of oral histories and many, many different topics. We have great public programs like tonight is. And we also feature a lot of help that we need and we get from various volunteer groups, one of which is something that we're featuring tonight, the Semiconductor Special Interest Group. You've got a little form in your chair, and we hope that many of you will consider joining that Semiconductor Special Interest Group. Along with semiconductors, we've done this for storage. Jim Porter is here, who chairs that one. Jim, where are you? Why don't you raise your hand if anyone's interested in storage. We have a lot to do with software in the background. Al Caso, our software curator, is here and is a person to contact, along with Bernard Puteau, who happens to be in France this evening. We're working also with the Web History Center. Mark Weber, would you raise your hand, please, to record web history. But our semiconductor group is a very special one because we want to give a presence of semiconductors in the context of computing history. And you're going to hear a lot about that tonight. Dave House, which I'll introduce in a moment, and myself co-chair that group, but we have a steering committee that's been working for probably the last year and a half on a number of projects. Michael Riordan, Harry Sello, Doug Fairborn, Dwayne Wadsworth, Jeff Katz, David Laws, who's our staff person on this project, Craig Addison, and Dag Spicer. All of us have been working together with some very specific projects that we'll be unveiling over the period of time to help advise the museum in terms of the timelines that are important, the things that we collect, and the stories that we want to be able to tell and put on programs and help sponsor programs like this. And speaking of sponsorship, I want to really thank, and let me ask for a round of applause for the Intel Museum, for sponsorship of tonight's event. And also, fundamentally, what a terrific exhibit that they have just opened up that you'll hear more of as time goes on. So with that, I want to introduce our moderator for this evening, Dave House, who is now chairman of Brocade and Credence. More importantly, of course, he is on our board of trustees at the Computer History Museum, many nonprofits that he works for. He previously was president and CEO of Allegro Networks and a 22 veteran of Intel. So many of you Intel people that are here this evening probably have worked with Dave and know him extraordinarily well. And with that, I want to bring Dave House on board, one of my mentors, one of the people I met that really made me come to the museum and motivated me and continues to do so. Bring on Dave House, please.
The year was 1971. Bread was 25 cents a loaf. A new car was $3,742. Gasoline was 36 cents a gallon. The average new home was $28,300. A stamp was 8 cents. The average income in the United States was $11,583. Minimum wage was $1.60. The president was Richard Nixon. Spiro T. Agnew was the vice president. The top songs in 1971 included Knock 3 Times by Dawn, How Can You Mend a Broken Heart by the Bee Gees, and Family Affair by Sly and the Family Stone. One of the other inventions in 1971 was the kicktail skateboard. There was a military junta where Major General Idi Amin seized control of Uganda. The Nobel Prize went to Willy Brandt in West Germany. Mao Zedong invited the U.S. ping pong team to visit Beijing, and a week later, Nixon ended the U.S. trade embargo with China. Anti-war militants attempted to disrupt government business in Washington in May, and military units arrested nearly 12,000. most who were later released. The population of the United States was 207 million people. There were a few interesting scientific inventions that year. An IBM team led by Alan Shugart invented the 8-inch floppy disk, or the diskette, initially designed for loading the microcode into the controller of the Merlin, which became the IBM 3330 diskpack file. It quickly became widespread accepted for program and data storage. RCA decided to sell its computer business after entering the computer business in the early 50s and later producing an IBM-compatible machine. They decided to call it quit in 71. And a little-known fact, the first personal computer actually happened before the microprocessor. The Kenback 1 was advertised for $750 in Scientific American in 1971. It was designed using standard medium-scale and small-scale integrated circuits. The Kenback 1 relied on switches for input and lights for output from its 256-byte memory. In 1973, after selling only 40 machines, Kenback Corporation closed its doors. We have one of those machines downstairs in visible storage. Also in 1971, first email was sent by Ray Tomlinson of BBN. Sent the first email when he was supposed to be doing something else. It's appropriate. Working on a different project. He's credited for being the one to come up with the @ sign for use in email. He sent his message over a military network called ARPANET. When asked to describe the contents of the first email, he said it was something like QWERTUIOP, which of course is the top row across the keyboard in the QWERTY keyboard. But there was another important event that you'll find if you check Internet files for 1971 and key events, and that was the Intel 4004. The first advertisement for a microprocessor appeared, the Intel 4004, in Electronic News. Developed for Busicom, which was a Japanese calculator company. The 4004 had 2,250 transistors and could perform up to 90,000 operations per second in 4-bit chunks. Federico Fagin led the design, and Ted Hoff led the architecture. That's what you'll find if you check the web. So some very important things happened in 1971. It's hard to think of the world without the microprocessor. But 35 years ago, the concept of putting a complete computer on a chip had not entered the realm of human thought. Now, for those of you who are interested in the history of the microprocessor, on your seat is a card for this DVD. This is put out by the Silicon Genesis Project, and it includes interviews with some 10 of the leading innovators and originators in the microprocessor history, and tells the whole history of the microprocessor, including the 4004. And Ted Hoff and Federico Fagin are on here, as well as Stan Mazer, Gordon Moore, Albert Yu, Dennis Carter, John Hennessy, Regis McKenna, Jerry Sanders, and yours truly. So you can go to the website and order this. It's an interesting view. You may have to do it in a few settings. There's a lot of minutes of video here, so please take a look at that, and I think you'll find it very enjoyable. So let me start out now by introducing our first speaker tonight. Ted Hoff, Marcian Hoff, was born in Rochester, New York. He got his bachelor's degree from Rensselaer Polytech in electrical engineering. Then he went on to get an MS and PhD from Stanford University, and he worked there as a research associate following that. In 1968, he became manager of applications research at the startup company Intel Corporation. It started just that year. Although Intel was founded to develop semiconductor memory, in early 1969 it contracted to develop chips for a family of calculators to be sold under the name Busicom. Hoff was assigned to be the liaison for engineering for the engineering team from Japan. While helping the Japanese engineers transform their design, Hoff became concerned about its economics and proposed a simpler design that included a simple general-purpose processor programmed to perform various calculator functions. The alternative approach was accepted by the calculator company, and it led to the first microprocessor, the Intel 4004. In '83, Hoff left Intel to become vice president of corporate technology at Atari, and has been since 1986 a consultant, first independent and now working with Techlicon, and is still employed there as chief technologist. Ted is listed as inventor or co-inventor on 17 U.S. patents. He's received numerous awards and recognitions for his role in the development of the microprocessor, including the Kyoto Prize, introduction into the National Inventors Hall of Fame, the Stuart Valentine Medal from the Franklin Institute, the IEEE Centennial Medal, and the Cleto Brunetti Award, the Silicon Valley Engineering Hall of Fame, et cetera, et cetera, et cetera. So with that, let me introduce Ted Hoff.
I'd like to start off by welcoming three very special guests here tonight, our grandchildren, Hannah, Connor, and Alex. Now, back in 1968, I was at Stanford University. And about the time that this article was appearing in the Palo Alto Times, I got a call from Bob Noyce, who's here on the left, saying that he was starting a new company and would I be interested in possibly interviewing for a position there. This was before Intel had a place to meet, so I interviewed at his home and ended up becoming employee number 12 at Intel. Now, Intel was set up to do semiconductor memory. Up until that time, the major memory technology used in computers was magnetic cores. These were typically little donut-shaped pieces of ferrite strung on matrices of wires, typically by hand. And the goal we felt would be to try to compete with them. They were several cents a bit, and they were making use of integrated technology to reduce the cost. But in about early 1970, the director of marketing and I put out an article in which we projected that we would get the cost of semiconductor memory down to less than a penny a bit by 1972, and we figured at that point we would take over from magnetic core. I might point out, we did overshoot that target in recent years. Now we're down to about a millionth of a penny a bit and still dropping. Now, it was felt that it was going to take a while for the computer industry to accept this new concept of semiconductor memory, and what do you do for revenue in the meantime? And one of the things that semiconductor companies did was undertake custom work. And so we were contacted by a Japanese calculator company that sold calculators under the name Busicom. They had a fairly complete design for a family of LSI chips that they were going to use to actually make a whole series of different calculator models. And in April of 1969, we signed a copy of an agreement over on the table over there. If one wants to see it, I have a copy of it. And in June of '69, 3 engineers came over from Japan to transfer their design, and I got the job of being their liaison, which basically meant they got a problem. I'm supposed to find out who in Intel they should go to solve the problem. Well, I was curious about their design, and I had been at those meetings in April, and I had an idea of what the target costs were for the set. And even though I was new to the semiconductor industry, the people there who were more familiar with things like packaging and chip design and so on were teaching me about the cost structures. And it began to look like it was going to be hard to meet the cost targets for this set as it was presented to us by the Japanese. Encouraged by Bob Noyce, I started looking at another design, and that had a couple of changes. One, it was more general purpose, more like a general purpose computer than the original calculator set. And the original set was based on what's called shift register memory, which uses 6 transistors per bit. And we were working with DRAM, and it seemed with 3 transistors per bit, which is what our technology at the time used, we could possibly do a better job, reduce the cost somewhat. We made a formal proposal in September of '69, and we got the go-ahead from the Japanese calculator company to go ahead with the Intel approach as of October. A contract was actually signed around February of 1970, and I believe I have a copy of that also here tonight if anyone wants to see it. Well, at that point, it was a concept, and I believe Dr. Fagin will tell you a little bit about how it went from concept to working parts. But he had working parts early in 1971, and we were able to show the Japanese calculator company that they were working. It took a while, but we actually persuaded Intel's management that this should become a regular product for Intel. And considering that Intel has been set up to be a memory house, there was a lot of opposition. It was felt that if we go into the computer business, we are going to look like we're competing with our computer customers, and they may stop buying memory from us and go to our competition. So there was a lot of discussion. But finally, the decision was made to announce the products, and November of '71, this ad appeared. And people have asked us, did we know what we had? I don't consider this a very modest statement. In other words, it was a pretty bold. Now, the 4004 came out then. I have copies of a price list that dates back to September of 1972. So this is about a year after it came out. And by the way, I don't know if you can see the fine print, but the 1103, which was a 1024-bit dynamic RAM, was selling for well under $10 if you bought a quantity of 25 or higher. So we had made the penny a bit target in 1972. And the 4004 in single quantities was selling for $60, and in 100-piece quantities, $30. So relatively inexpensive for a computer when you compare it to what we had dealt with maybe a decade before. Now, in 1961, while at Stanford, I had the opportunity to work with an IBM 1620 computer. This is what one of them looked like, at least part of it, the console. The performance of the 1620 was about 2,000 5-digit decimal additions per second. That's about the same performance that a 4004 system would offer, in the same order of magnitude. Now, the 4004 was, just the CPU, and you had to add other things to it. But consider that you got the CPU for $30 if you were buying a number of them, or $60 buying just one. For the IBM 1620 back in 1961, a decade earlier, we paid $2,500 a month to lease that machine, and that was at Stanford. We were getting a 60% educational discount. So other people would have paid 2.5 times that. Now, in addition to the processor, we also offered design aids. And we called these the SIM series of boards, and we had one of them was a SIM 402. It was a single board computer, and you could plug in to up to 16 of the 4002s, which gave you 1,284-bit quantities. And those, they could be thought of as either binary or binary coded decimal digits. You could plug in 16 EEPROMs for up to 4K bytes. And so that cost, fully loaded in small quantity purchases, would have cost you about $2,400 one-shot cost. Now, to put it in perspective, compared to the 1620, it had maybe only a fifth of the amount of memory. But here you paid for it once, not every month. Performance was similar. Now, people would say, well, what about the personal computer? We were not ready for the personal computer at that time. In other words, there were a lot of other things that were needed, and memory was still a major factor. When you consider the major difference between the cost of that board loaded and the CPU is the cost of the memory that went on to it. So it took a while for other parts of the system, for memory to come down farther before the personal computer. Our market, we saw, was what we now call embedded control. Now, I might point out, we have a SIM 402 system sitting on the table over here. In 1972, we tried to interest a different kind of manufacturer in the possibility of using microprocessors. That was, I believe the company was Magnavox, which made an analog video game. And we thought there ought to be a business for microprocessors in video games. And we talked to them about it, and they were not interested. Their microprocessors are way too expensive. Well, so it wasn't long after that that there was quite a market there. But if you want to see the demo afterwards, we have a demo of a working SIM 402 with an original 4004 in it. And this was a replica of a demonstration that we did back in 1972. So that's where we were in 72. Of course, a lot has happened since then. And there was also many steps that it took to make the processor happen. I believe Dr. Fugine will tell you about some of those. So.
Thanks, Ted. We'll hear more from Ted here in a few minutes. But next, Federico Fugine. He was born in Italy. He attended technical high school there. He went to work for Olivetti, and there he designed his first computer by the age of 19. He then went to the university where he got his doctorate in 1965. Not too long after that, he went to work for SGS Fairchild in Milan. There he developed a method of manufacturing metal oxide semiconductors, MOS integrated circuits, as well as designing the first two commercial ones. In 1968, he left Italy for the United States to work in Fairchild's parent company back in Palo Alto, California, which had been founded, of course, by Gordon Moore and Bob Noyce and others earlier. While at Fairchild, Federico developed the silicon gate technology. This, of course, replaced the aluminum control gates, which were used at that time and made for faster, lower energy, less space, lots of good things. And, of course, today, silicon gate is the primary technology that's used in integrated circuits. In 1970, Fugine moved to a new company, Intel, where Noyce and Moore had gone 2 years earlier. He was eager to return to designing circuits, and Intel put him in charge of designing an integrated circuit for Busicom, the Japanese calculator company. So he'll tell you more about that when he arrived, but along with his colleague Ted Hoff and Stan Mazer, he envisioned this single chip that performed the functions that had been performed by numerous chips before. The result, the 4004, the first microprocessor. In 1974, Federico left Intel to form Zilog Corporation, which he founded. He co-designed its most famous product, the Z80, conceived of the 8008, and very much involved in the Z8000. More than 1 billion Z80s were eventually sold, and it remained in production. Well, it's still in production today. After the company was acquired by Exxon, he left and co-founded Signet Technologies, which builds intelligent voice and data peripherals for personal computers. And in 1986, he co-founded yet another company, Synaptics, which specializes in neural network technologies as well as computer-human interfaces devices based on touch, sound, and sight. This allows computers to adapt to human behavior rather than forcing users to adapt to the computer. He's still chairman of the board. In 1988, he's got tons and tons of awards. He was awarded the Marconi Foundation Fellowship for his work on the microprocessor. In the same year, he was awarded the Gold Medal of Science and Technology by the President of the Government of Italy. In 1994, he received IEEE W. Wallace McDonald Award for his work in silicon gate technology and microprocessors. And in 1996, he was inducted into the National Inventors Hall of Fame for the co-invention of the microprocessor. Federico.
Well, thank you. It is really a pleasure to reminisce about the microprocessor. Let me start with the MOS technology in 1968. Basically, in production, there was high threshold metal gate MOS technology. That was pretty unreliable, relatively slow technology. To make complex random logic chips, we had to use 4-phase designs. Really, there was not much that could be done still with MOS technology in 68. However, there were two key technologies in development at that time. One was low-threshold metal gate MOS with ion implantation. That's the technology that MOSTEC developed, and that was really the mainstream technology for a number of years. And self-aligned silicon gate MOS technology that was developed at Fairchild. I was in charge of that project. And that project was completed in 1968. A paper was given at the International Electronic Device Meeting. This paper described the technology and also an integrated circuit, a commercial integrated circuit. There was the 3708, the Fairchild 3708. This technology was then adopted by Intel and became the basis for semiconductor memories and the microprocessor. Now, in April 1970, I joined Intel. The day that I joined Intel, Stan Mazer showed me a block diagram and the basic specifications of a 4-chip set that was to be the BISICOM project. There was the 4-bit CPU, and the basic architecture and the instruction set was pretty much completed. There were a few loose ends, which I completed later on. But basically, the specification was done. The design of the chips was supposed to have started in October when the agreement between BISICOM and Intel occurred, but no work was done since October. So I had the honor of being 6 months late the day that I started on my project. On top of that, the following day, Masatoshi Shima, which was the BISICOM engineer, was arriving from Japan to check the designs and was supposed to, of course, at that time verify the logic design. The logic design of the 4004, which was supposed to be in layout. In July 1970 was when the entire chipset was supposed to be completed. So Shima arrived. He said, I'm here to check. Where is logic? And I said, I gave him what I was given, this block diagram and this stuff. And he said, no good. I had this. This is only idea. I want logic. And I said, I don't have any logic. You bad. I said, I've just arrived here. I just was hired yesterday. You late. And so I was baffled. And of course, at that point, there were a number of very agitated phone calls between Shima. He was in my office. Ted Hoff, Stan Mazer, myself, and Shima were in the same office. And in Japan. And I could tell by the tone of the conversation they were not very gentle phone calls. And basically, in the meantime, I tried very hard to figure out a time schedule that would really minimize the delay that was incurred by Intel. So I basically put a schedule together that gave December 1970 as the date at which I could give all 4 chips, samples for all 4 chips. This was really working very hard because 9 months for 4 chips, of which 3 were state-of-the-art chips, was really, really pushing. Of course, I had to go do all this, logic, circuit design, layout, Ruby cutting, all this stuff. And I decided to stagger the chip development, starting with the 4001, and then while the layout of the 4001 was going on, the design of the 4002 would occur, and so on, so that by December, we would have all 4 chips. But to do that, I needed an engineer to help me, and also adequate layout and technician support. I was by myself. I had no engineers, no layout people. That's it. I had to do it by myself. So I asked Shima to convince his management to let him stay for a while until I found an engineer if he wanted to, if he wanted to get 1970 to get the chips. That's what was required, and the management decided to let him stay. So he stayed until October 1970. Now, in 1970, also, Intel had no expertise in random logic design. There was no methodology and no infrastructure for random logic design. Companies like Fairchild or TI, they had specialized cells, they had circuits design, they had computer programs to help with logic simulation and chip design and so on. None of that was available at Intel. On top of that, the random logic design with silicon gate required a different style than metal gate. So basically, I had to start with developing the basic methodology. I did that by deciding that I was going to use a 2-phase design, but that required bootstrap loads. In those days, bootstrap loads were considered unworkable with silicon gate for a variety of reasons I don't have time to go through. But I made it work. Then I decided to use buried contact, which is an invention that I made at Fairchild a couple of years before, which allowed to make direct contact between polysilicon and junctions, so that you could have effectively a 2-layer of interconnections, making a very dense circuits. I also devised a graphic design that would allow to size transistors very rapidly, because I didn't have time to do any simulations. I designed all the basic building blocks that we're going to use for the family, so that we had that as sort of building blocks. And then I combined the logic design and the circuit design into a single document. In 1969, what people would do, they would do this, a logic design, then transfer that into a circuit design, then from there into the layout. And of course, every time you transfer from one set of documents to another, you can make mistakes. So I decided to avoid mistakes, to combine logic design and circuit design, and do that in a single sheet, in a single design, but also taking into account the layout. So the transistors would be put as close as possible to their physical location in the layout. Then, of course, I designed for testability, which was clearly very important. And I tried to do that by minimizing computer simulation time, because Vadez, my boss, told me, don't use computers, very expensive. So the result of that is, in October, on schedule, the 4001 was designed and came out and worked first time. This is 1K bit, another K bit, metal mass programmable. This part is the so unique aspect of the chip that has to do with the family. There is a specialized I/O that are programmable by metal here. This is the 4-bit bus drivers for the data bus. They need to drive 150 picofarads, so they have to be pretty heavy transistors. And the rest of it is pretty much a ROM. This is the 4003. This is the simplest of the 4 chips. It's a 10-bit shift register. This was done in our spare time. And this is the 4002, 320-bit of dynamic RAM, 3-transistor dynamic RAM, self-refreshing. The refresh counter is here. All the I/O port and control and timing, specialized timing is here, and the rest of it is similar to a typical memory. And finally, the 4004. Here I'm showing an example of the type of document that contained the circuit design and the logic design that I mentioned early. Here, for example, this is the instruction register. This is the instruction decoder, the encoder. This is the control logic for the index register. Notice that all the transistors have a little number you can actually not read, but that's the size of the transistor. That's what I use the graphic design to size all those transistors without having to do any simulation. Here, by the way, that's the 4-bit bus that goes inside the chip and controls the rest of it. Here's an example. This is just a corner of the chip. You can see here for example, those are the big data bus drivers. These little pink squares or rectangles, those are the capacitors of the bootstrap loads that were absolutely essential to get the performance out of the chips. And here, for example, you see very contacts, and you see metal running over the logic, so that in fact you have logic underneath and metal connecting on the other layer, therefore achieving about twice the density of metal gate technology and 4 to 5 times the speed of conventional metal gate technology. And finally, here's the entire chip. You can see here's the instruction register, the instruction decoder, the control logic of the 2 memory blocks. This is the index register, 64-bit. This is the stack pointer, the program counter, the incrementer, decrementer is here. This is the ALU, the control logic of the ALU. This is the timing. This is the control logic for the external memories, and this piece also. And this chip was 3 by 4 millimeter, and those are my initials, by the way, FF. So basically, I was pretty much on time, probably a couple of weeks late, but late December 1970, I received the first wafers of the 4004. I load them up, and nothing happened. And I go to another die, nothing happened. And I was thinking, oh my God, how could I have screwed up so bad? You know, the other 3 chips, by the way, worked first time, except the 4002 had a couple of very simple mistakes that were immediately cleaned up. Basically, I found out that one of the masking layers, the buried contact, was left out of the processing. And so a good 30% of the gates were floating, and so that's why nothing was happening. So finally, I got the new silicon about a month later, and I received the wafers toward the end of the day, and I loaded them up and started testing, and everything seems to be working. I kept on working and working and working. Eventually, by 4 o'clock, I was really tired. But I was also very happy because everything that I tested was working. So I went home, and my wife was waiting for me, and I said, Elvia, it works. And that was the night that the 4004 was born. Then a few weeks later, I found out that there were a few minor mistakes which were corrected, and eventually in March 1971, we had fully working 4004s. Now, in the meantime, Shima, they went back to Japan in October, worked from October to January to develop the firmware of the calculator, and he gave us ROM patterns that were supposed to be, masks were supposed to be made for the 4001s in February, so that by March, all the chips ended up in Japan, and the first prototype of the calculator ended up working completely. This is the prototype of the calculator. The PC board is underneath this printer here. This is a Seiko printer. There are about 10 4000 family chips underneath. This was a gift to me, a personal gift to me, by the president of Visicom, Mr. Kojima, because basically I worked 80 hours a week to make up the delay of 6 months that was incurred in the project. And by the way, in the middle of 1971, Texas Instruments announced a CPU on a chip. There was actually the TI version of the 8008, and that was announced only a few months after the 4004 work. So timely execution was the key to get the first microprocessor at Intel. By the way, this is now my gift to the Computer History Museum. So we went. So from March, the end of March, until June, we completed the characterization, the transfer to production, a lot of work to produce the chips. And then in early 71, I decided to design and build a tester to making to testing wafers of 4004. And I decided to use the 4004 as the controller, as the microcontroller, you would say today, of the tester, for 3 reasons. Number one, I thought it could do the job and make my life easy. Number two, I could show to Intel management that you could actually do an application that was a control application for using the 4004 instead of calculators. That was the original aim of the family. And number three, I wanted to show that an outside engineer, like a customer, what it could do to develop a system using the 4000 family. So with that, I used the 1702 EEPROM chips that were a new invention of Intel, the programmable, electrically programmable memories. And with that project working, that gave impetus for all of us, including Ted, to convince management to really commercialize the 4000 family. But we couldn't do it because Busicom had an exclusivity for the 4000 family. So we had to have some kind of rescission of that exclusivity. And I was happy to find that Busicom was in difficulty by talking to Shima, and I proposed to Ted to Noyce to actually give a price concession to Busicom in exchange for the exclusivity. The bottom line is that by the middle of the year, the 4000 family, the decision was made by management to introduce the 4000 family under the name MCS4, and the product marketing organization was created to handle the product. Hank Smith was the manager of that product marketing organization. And finally, the announcement was made in November. You've seen this before. This is one of the few ads where the hoopla here was probably not, was actually truth in advertisement. There were a couple of papers published soon after the announcement. This was the first one early in '72, Region 6 conference at IEEE, the MCS4 LSI computer system, and then Electronics in April published another article by myself and Ted. So this was the beginning of the marketing of the product. Now, I want to acknowledge many other contributors to the MCS4, in addition, of course, to Ted Hoff and Stein Mazer, Masatoshi Shima. We talked about these people. Alfine and Yang Feng helped me in the characterization and test programs development toward the end of the year and early part of '71. Paul Metrovich and Charlie Corbin helped with the testers' implementation, the characterization work, and so on, starting in the October-November timeframe. Rod Sayer was the first draftsman that I hired. He never designed a chip. He actually was a mechanical draftsman from Lockheed, and I had to teach him how to design chips. Barbara Manis and Julie Hendricks, however, had done designs before, so they were quite helpful. Not a Rod Boson, but he actually took a few months to learn. And Hank Smith, of course, was the first product marketing manager. They made a tremendous contribution to the success of the microprocessor. The rest is history. Thank you.
Now, Masatoshi Shima is very well known in the microprocessor business in the early days, and his role starting out at Busicom has been mentioned. Here's a picture of him on the left wearing his Intel badge, and here's a picture on the right of him today. Now, in the Semiconductor Special Interest Group, I co-chair with Jack Bush the microprocessor subcommittee, and we've been busily creating video histories of the teams that designed some of these early chips. And so Shima was a key person to find, and so he launched a search this year for everybody who might have known where he was. And finally, after a number of different queries, we were able to get in touch with him by email. And he wanted to say that he's sorry that he couldn't attend this evening, but he had a wedding ceremony this weekend, and he had to give a lecture at the university early this week. But he asked if someone could read a statement from him at this event. So let me read the statement from Masatoshi Shima. Congratulations on the 35th anniversary of the Intel 4004 microprocessor. The world's first microprocessor, the 4004, was co-developed by Busicom, a Japanese manufacturer of calculators, and Intel, a U.S. manufacturer of semiconductors. The success of the 4004 development is attributable to the cooperation between engineers of various development fields, applications, computers, software, LSI, etc. By exchanging their expertise and ideas in an interdisciplinary way, and by addressing the great many problems with patience and a challenging spirit, these engineers sowed the seeds of a new technology and grew a finished product. Microprocessors became the technology to open up a new era. And it had two outstanding impacts. First, the microprocessor opened up a new era of program through replacing software, the hardware logic circuits comprising ICs of the former era of logic. This led to the development of intelligent microcomputers. At the same time, the microprocessors allowed young engineers to access the power of computing, permitting the innovative development of the personal computers and computer games, which in turn led to growth in the software industry and paved the way for the development of high-performance microprocessors. I believe the 4004 development was the destructive innovation. I enjoyed 4004 development project very much, so I became the first logic design engineer, the first application engineer, and the first customer of the microprocessor. Many thanks to all of you. There's another person who's been mentioned quite often, that's Stan Mazer, who worked for Ted Hoff at the time. And Stan has been involved here in the museum. Unfortunately, he had a previous commitment with his son in New York City for this evening, and he wasn't able to be here. But recently, as part of our microprocessor subgroup of the semiconductor SIG, we were able to get some comments from him. And from that video made for historical reasons, I think we've got a short segment we can show right now. Do we have that ready? I'm not seeing it yet. So, David, could you give me the high sign? Is it ready? Okay, let's go.
Anyway, I ended up working at Fairchild on computer architecture and decimal floating point unit. And I was recruited by Ted to go to work at Intel when he was working on the Busicom project. I joined him in September, and that project was underway already. One of the things that was quite clever about Ted's management style is that he posed a question to me. He said, well, if you wanted to do a computer on a chip for Busicom, what would you do? And I've been working on a very large-scale computer, and my thoughts were really in another arena. So I thought a little bit about it, and I came back with some proposals that were pretty far away from what we actually did. And I think it was quite smart of him to have me thinking about it independently, but he had already done a lot of progress by September on the 4004 design. I was working at Fairchild on a very fascinating high-language computer, and Ted offered me the job to work on memory systems. Now, memory systems are pretty dull. And so I thought, well, this is a fascinating company, and it's a good guy to work for, but it's going to be awfully boring working on memory systems. So it's kind of ironical that sometimes I like to say you do the right thing for the wrong reasons or the wrong thing for the right reasons. And so this turned out to be, of course, the high point of my career working for Ted on the microprocessor, which was a surprise to me when I got there. So it's pretty obvious to us that we had a universal part that could be used for many applications. About the only application that I think we clearly didn't think about was the home computer. We never figured out why you want to have a computer in your home. And you're in the opposite direction. One was someone calling out and saying, I work for the phone company, and I'm going to quit my job and do something with this component. Someone was extremely enthusiastic about it. And someone else who would say, I don't believe you have a computer on a chip. This must be just an arithmetic unit or some mistake or something like that. So I would go from start belief to start disbelief. Well, I think just a couple of anecdotal things. When we created it, it was obvious, us having worked in computers for years, that this was a general purpose gadget that could be used extensively. But I remember watching the stock price on the market, and an announcement was made, and it didn't move a quiver. In other words, the significance of the components that Intel as a corporation wouldn't happen for years. marketing campaign, we did a couple of clever things for marketing, and one of them, we called it the alternative. And the idea of this is an alternative to logic design. So what we're trying to do is convert logic designers to programmers. From a broader viewpoint, in fact, reflect that when you're in the memory business, you help to sell dynamic RAM chips, which Intel was making. You're just a few computer companies that were there, let's say IBM, GE, RCA, Xerox. You only need one or two salesmen, and it's a commodity kind of product. It gets designed in, and then they use a lot of it. Microprocessor was almost the antithesis. You ended up having thousands of customers, each of which needs some degree of support, and whose applications for the computers might only be a few thousand. So it was a completely different positioning for the product and the kind of company my customer had originally proposed.
Thank you. So we're going to open up the floor to questions a little bit later, but let me ask a few questions of our panelists to start out with. So phenomenal accomplishment in semiconductor technology, but we all know that without software you don't get anywhere. Tell us the story about software for the 4004.
Well, it was a problem because, for one thing, there was a quality of, prestige was associated with a big computer. And we get one of these young kids out of college, and they're the ones that are the most creative in generating software. And they'd find out we wanted them to work on something really small, and they'd say, I don't think we're interested, and they'd leave. So it was really a problem to get people to come and work for us. We actually, I think, got some software done for us by colleges where we would agree to trade some hardware if they would write something for us. So we'd give them a sim board or something like that for a piece of support software. And we had a few people inside that did some work for us. After the media discovered the microprocessor, the whole thing turned around. Then we had those college students coming and begging to come and work for us. But before that, it really was a problem.
So what size wafers did you make this thing out of? What was the?
Oh, actually, I have one. It's
how big were the die?
2-inch wafers.
2-inch.
Yeah, all of 2-inch. Now, of course, it's 12-inch wafers, right? So this is the state of the art in 1971, 2-inch wafers. And so, of course, you couldn't fit a lot of chips, even if they were small. And improving the yield was a big deal, of course. So that's.
You know about how many were produced?
4004.
Yeah.
I would give a wild guess.
At an order of magnitude number?
Order of magnitude, right? Probably around 1 million.
Uh-huh.
Yeah, it was not a huge runner.
Then
the 4040 took over after the 4004. There was probably another, maybe 600,000, 1 million of those. That was the end of life. I mean, it was not. It was very important because it set the stage for the industry. But in terms of commercial success, it was not the same commercial success of the 8080, for example, or the Z80s, those early microprocessors.
How about Busicom? Did they use the unit?
Busicom bought about probably a total of 60 to 100,000. And of course, in 1971, Busicom was the largest customer of Intel, and in 71 was not a good deal for Intel. It was a recession. There was a recession at that time, and Busicom really, and the 4000 family was the most profitable components that Intel was making. So Intel actually made a ton of money because they were selling those at $70 a kit.
So what other applications?
Well, the first applications that I remember after the announcement, pinball machines, traffic light controllers, cash registers, bank teller terminals. What else? A blood analyzer. A company in Denmark was doing that. Those type of products.
I remember two. One was fairly ordinary. People were outfitting gas stations with recording devices that would report back at the end of the day how much gasoline had been sold for inventory control. But maybe a more interesting one was there were some farmers that had outfitted cows with collars with microprocessors in them to record how much the cow drank and how often it went to the salt lick and things like that to try to correlate it with milk production. So microprocessor outfitted cows.
Actually, the most remarkable application, of which I feel very, in a sense, very proud. I mean, is the 4004 is one of the few artifacts that have gone beyond the asteroid belts in Pioneer 10.
Is that right?
Yes. Yeah, it's a major piece of our work up in space. And now if it doesn't work, who cares?
Ted, you referenced this earlier, that here you got a memory company that was formed to sell memories, and now you've got an altogether different kind of a product. You ran into some resistance. Who is the real champion that saw the commercial benefit here and took it through to the point where you actually can produce it?
Well, I think the real champion was Ed Gelbach. Ed came to us in the summer of 1971, and he came to us from Texas Instruments, and as Dr. Pagine mentioned, TI was doing some work in this area, there were some connections to work we had done that got to TI and got them into the area. But anyway, I think Ed knew what was happening out there in the industry and figured we should be first. And so I look at him as being probably the one who was most instrumental in overcoming the objections. But I had some of the earlier marketing people take me aside and give me the argument and said, look, we're late to the business. The mini computers are out there. They sell 20,000 machines a year. When you're late to the business, if you get 10% of the market, you're really lucky. That would be 2,000 chips a year, and it's not worth the bother. Well, I think it was Dr. Shima a few years ago came back and told the number of microcontrollers used in Japan that year was something like 600 million. So the market turned out to be more than 2,000 chips a year.
That's a case of underestimating the market size. So were there ever any high-level languages developed for the product, or was it simply an assembler language programming?
I think for the 4004, as far as I know, it was just assembly language. Some people may have done something, and actually even some of the calculators had a degree of programmability built into them, so you could almost argue that had the rudiments of a high-level language. But it was more when we got into the 8-bit processors that we started to really do some development of higher-level languages.
And of course, the 8008 followed the 4004 by how long?
They were almost done in parallel. We started, as you saw from that, we got the go-ahead for the 4004 in October of 1969. The contact that led to the 8008 was only about 2 months later, in December, and we wrote the target spec for it very early in 1970. But it turned out that the 4004 and the 8008 had some overlap, and Dr. Pagine could probably give more detail there. But the 4004 was done first, and the 8008 came out a few months later. So I think we announced the 8008 around April of 1972.
Yeah, it was 1 year apart. I mean, one was March 71, and the 8008 was April 72. It was restarted really in January of 1971.
The 8008.
The 8008, after I was pretty much done with the 4004. And Hal Finney was the designer of the 8008 under my supervision. So
this required an altogether different kind of marketing activity from data
Well,
sheets?
but
and
it was very similar to the 4004.
No, I mean the
concept and so on.
microprocessor
Yeah.
versus the
Oh, yeah.
classic products. of
Absolutely,
Intel.
absolutely. I mean,
We're
you know,
producing.
data sheets were supposed to be much more application-oriented. They were really books as opposed to being one sheet or two sheets of specifications. And back to the question of high-level language, the PL1 was the first high-level language that was developed by Gary Kildall, is the founder of Digital Research, I think was the company, and also the developer of CPM operating system. It was the first one to create an operating system for a for a computer using microprocessors. And he did that for the 8008, and then it was extended to the 8080.
Was there any relationship between the control program or operating system in those machines?
What do you mean?
There was something that ran on the Intellect 4 and there was an Intellect 8.
Well, the 8080 was machine code compatible with the 8008. So any software that was developed for the 8008 would run on the 8080.
Mm-hmm.
However, the 8080 had features that made it much easier to do some of the things that were very difficult to do on the 8008. So probably most people would want to upgrade their software in moving. Even though there was nominal upward compatibility, generally you'd want to rewrite to take advantage of all the extra features that the 8080 had.
Yeah, the 8008 was a pretty stripped down microprocessor.
So what was the biggest shortcoming of the 4004 instruction set? I mean, when you always learn going forward, as you did from the 8008 to 80, what was the biggest shortcoming of the 4004?
Well, the way you were addressing data, I mean, it was really very awkward. It was a ROM-based machine, so storage, the RAM storage was really pretty much for data. Though you could use some of the data as instructions, so you could kind of get away with it, but the addressing scheme was really awkward.
Was that based on the original application and the calculator?
Based on the calculator application, yeah.
That was a fallout from the calculator application. The other thing, it was a Harvard architecture with separate program memory from data memory, which tends to keep you from doing things like developing compilers and so on in high-level language applications.
Yeah.
Okay, well, I want to make sure we have time for questions from the audience, but we have one more chair here and one more person, so I've got an introduction to make. Tim McNerney is a senior engineer at Retica Systems, a venture capital-based startup that designs ocular biometric systems. He's got a master's degree from the MIT Media Lab. From conception through construction, Tim has assembled and led a talented team of engineers and designers who created the Intel 4004 35th anniversary exhibit at the Intel Computer Museum, and I hope you all go there and see that. Critical to the success of the project was the digital archaeology, a new term that obviously here at the Computer History Museum we're very interested in. Those efforts to perform in collaboration with the Computer History Museum. Tim will talk about the process of reverse engineering the Intel 4004 schematics and the BusyCom 141PF calculator ROMs that led his team to uncover elegantly crafted layers of a computational system that makes optimal use of limited hardware and software. Tim.
Thank you. Thank you. It's really apropos that I'm speaking here because without the Computer History Museum, we just could not have done this project. That gift that Federico Fagin talks about, that calculator relic that he donated to the Computer History Museum, contained socketed ROMs that was really the only historical artifact that we could have extracted the BusyCom software from. And so without Federico's help and without the Computer History, Dag Spicer and Salam Ismail, we just couldn't have done it without them. So we really thank you guys. It's a great place. And what can I say? The other thing that I think is just great is that how can you be talking about historical innovation only 35 years ago with the inventors all living. It's just amazing to have a living history like this. It's just great. I got interested in computers in the late 60s when I was, I don't know, maybe 6 years old. I knew I wanted a computer when I grew up and could afford a house that I could fit the computer in. And then, I moved from Italy, where I lived, to Silicon Valley, and had the fortune of being able to have access to computers. I remember fondly the husband of my French teacher, who worked for Hewlett-Packard, who would bring home calculators, pocket calculators, big calculators, and lend these to me over the weekend so that I could learn how to program. And I eventually learned how to program a PDP-8 and various machines after that. I guess what would you call me in this case? I was introduced in my sort of professional hat, what I do at my job. But in this case, I'm a history detective. And it was really a very interesting journey because we didn't really know what was available. We didn't know what was in the Intel archives that could help us with this project. We never really had any idea that we'd be able to find the software for the calculator. So, things started out modest. We had really no idea what kind of resources we were going to find along the way. So I did a lot of research in, what the 4004 was about, who the people were, et cetera, and that really helped, know what to look for. So let me give you sort of an outline of the talk. I'm going to tell you a little bit about the project and give you a little bit of historical perspective. How did people do engineering back then, and how did people do engineering now? It's quite different, really. Maybe a few words on the educational value of this kind of these kinds of designs, being able to go back to the vaults, go back to the archives, and have material for people to study. So what do we do? Well, I first approached Tracy Mazur at the Intel Museum with a crazy idea. I wanted to build a chip that people could see to make the invisible visible. And how would I do that? Well, these chips were pretty small, 3 by 4 millimeters. The transistors, very tiny. And I wanted to make something big, say this big, so that you could actually see the transistors with the naked eye. And this is what I pitched to them. I pitched to them a fully functional replica of the 4004 using discrete transistors surface mounted onto a printed circuit board about 16 by 22 inches. This is the sort of the flyover version, and all the black dots are transistors. And this is the silk screen of the original Maskworks, and then printed circuits underneath that. It was something that I thought I could do alone, but it turned out to take a team of about 4 or 5 people in addition to myself, software people and hardware people, electrical engineers, mechanical engineers, to make this exhibit, graphic designers, exhibit designers. It was really a collaborative effort, interdisciplinary effort. So we started by reverse engineering. I went to the Intel Museum, I went to the corporate archives, and Rachel Stewart, the corporate archivist for Intel, was able to dig up the check plots, these sort of binders with transparencies in them that have not the original Maskworks, but colored plots that you could sort of look at the different layers and see how they lined up. She found the schematics. Federico and I went to the Intel archives, and it was such a fast thing. I had no idea how big these schematics were, how many there were, how many drawings there were. So Federico sits down at this table, and Rachel hands them 3 sheets of rolled up vellum, and he goes, 1, 2, 3, yep, that's all of them. And he said, see, these schematics are drawn just like the chip is laid out. And that's really something that, to me, is great about this, is that you can really look at the functional units. It's not, a vast city that you don't understand. You can really see the functional blocks with your naked eye, here on your naked eye through a microscope for the original chip. So that was great. So now we had the schematics, and eventually they found the mask works. And what we wanted the mask works for was we wanted to lay out the printed circuit board really as close as possible to the original chip. And in fact, that's what we did. We were able to, thanks to Fred Hittig, who's my electrical engineer here, he did schematic capture using modern CAD tools to capture the schematics that we had drawings of. I had two engineers in Canada who are really sort of software experts, Brian Silverman and Barry Silverman. Actually, Brian Silverman is known to the Computer History Museum because he helped with the PDP-1 project, resurrecting arguably the first video game, the PDP-1 Space War. And he's no stranger to reverse engineering. So we get the schematics, and Barry and Brian just eat it up. And they had no idea what to expect either. And the thing that they really enjoyed about this was that it was so simple. It's really, the minimal microprocessor. Okay? Anything less is not a microprocessor, and anything more is more complicated. So first they started staring at the diagrams and trying to follow the traces, and then they made a simulation of it, a transistor-level simulation, which is available at our website, 4004.com. So there's an animated simulation that you can see. You can see the transistors turning on and off, and the wires turning red to green, logic false and logic true. And they used that to understand better how the processor worked. And within a couple of weeks, they deeply knew this design and really had a lot of fun doing it. So when we went back to making the board, we had corrected schematics. We had schematics that we knew worked. We had designers who knew how this stuff worked. And so when Fred went to do his schematic capture, he had good schematics to work from without any kind of typos. It's worth noting that this project was done with really no CAD, essentially. There was some simulation. I don't want to talk about things that these guys can talk about, but there was some simulation tools, sort of what we might call on the SPICE level, that Fajin and his team used to understand, how the transistors would work and what size devices to use to drive different sized buses, et cetera. But that was about it. And I think, I guess they also did, instead of using simulators the way we do today, didn't the guys at Busicom actually make some sort of discrete, yeah.
For design, because it was done afterwards so that they could develop the software.
Okay, so it was really
Busicom. So it was done subsequently to the 4004 design.
Oh, okay, fine. So that wasn't really a design verification
It was not
step.
a design verification. It was simply a tool to allow them to develop the software.
Right. So the design verification, from what I understand, was that these guys looked over the plots made out of Ruby.
It was actually steel trap mined. Shima could find any mistake that you could possibly make. It was unbelievable. So Shima was the computer-aided design.
So what Fajin is referring to is staring at small sections of the mask works. I think that they were about 1 meter by 1.5 meters.
Much bigger.
Much bigger. How big?
It was 500x. So
500x.
Yeah.
Okay, thank you.
So it was 2 meters by 175, 150. Yeah.
That's why it's great to have folks around. So anyway, yeah. So these guys didn't really have any CAD, and we did. So we were able to immediately simulate the processor and get it working. A small piece of software. And so that was sort of the beginning of the reverse engineering effort. The other piece of the reverse engineering effort really only started when we got our hands on the software. So that's sort of back to where the Computer History Museum came. There are very few of these calculators in the world. I want someone to correct me, but my understanding is under 10. I guess there were, what, 60, 100,000 of these things built, but they got thrown away or something. Old business machines just go to the scrap heap. So there aren't very many of these things. And in particular, the one that the Computer History Museum has socketed ROMs. Fajin was so kind to give me several 4001 ROMs, one that I could keep and destroy, as I put it, and 4 that I had to treat like, sacred things. And those were the Busicom ROMs, but it turns out after I made this custom-made ROM reader that they had holes in them. There were sort of pieces of zeros that the chips were defective in some way, or maybe the storage or something like that. So we had sort of 80 or 90% of the software. We could tell something about the software, and we knew that the ROM reader was right. And then I sent Fred to the Computer History Museum with the ROM reader, and we got the actual flawless bits, which are still on display. You can't see them, but they're on display. So then, again, we have the bits. We get them back to Barry and Brian Silverman, and again, they eat this for lunch. And within a couple of months, and these guys are just working on weekends. They have day jobs. They had stared at the disassembled code, sort of figured out how it was working. Then they made a simulator where they simulated all of the hardware. Fred had traced the wiring diagram from this relic. I had photographs from a collector in Germany, Christian Bassau. He had a calculator that he had taken the front and the back side of the printed circuit board, and I made kind of an X-ray diagram of the two so you could see all the traces. So I had traced the circuit board. We had sort of now a lot of the hardware, the wiring diagram. We knew something about the printer and how the keyboard was wired up. And these guys made a simulator in Java that would let them get the calculator working completely in software. So that was absolutely indispensable when we were then going to do this in hardware. So it's just fantastic to have a team of people who are so enamored with reverse engineering. And some of the things that we found out were really that this is a nice layered design. The statement from Shima talked about interdisciplinary. Well, we have device physics, we have computer architecture. Shima came from, I think, a software background. He was really a man of many hats. And these guys all work together not just on their own layer. Shima helped Fajin with the design of the chip, and Stan Mazer helped with some parts of the software. They were working across a bunch of different layers all at the same time to make the minimal amount of hardware, the minimal amount of software, the minimal amount of printed circuit board. Nothing was sort of under-engineered. It was really just optimal. And part of this, I think, is because the parts were expensive. Someone's going to correct me if I'm wrong, but I understand that in 1971 dollars, the 4001 ROMs were about 5 cents a byte. And if you scale that to modern dollars, that's 20 to 25 cents a byte. So, an extra ROM, that was a lot. 256 byte ROM. You didn't want an extra 256 byte ROM. So, talking about the layers, there was the processor layer. Then they built stuff written in 4004 code. And what they did with this little 4004 code plus hardware, the chipset, was they simulated the machine that Busicom came to Intel in the first place. Busicom, they had a fully fleshed out design that was this calculator machine. It was special purpose, just this particular product. It used shift register memory. It had a ROM for control store. And it was a much bigger machine than the 4004 and the associated chips. They didn't want to abandon that design. And what they ended up doing was using the 4004 plus, let's call it microcode, to make a virtual machine that was now this calculator machine. If anybody watches Doctor Who, it's, the TARDIS, right? On the outside, it's the size of a phone booth, and on the inside, it's the size of a TV set. So you know, it's just a fantastic case study of layer across layer engineering. This is very different than how people do design these days. First of all, significant designs are never done by a team this small. I mean, this was a small team. We saw all of the, you know, sort of helpers and draftsmen and the like, and we don't want to discredit them, but the core of the team was 4 people. And that's just unheard of, right? And they did it in a very short amount of time, and they all worked together. Nowadays, as Brian Silverman likes to say, abstraction is king. And I think, you know, abstraction is great. Abstraction barriers, it gets taught at MIT, and APIs and you know, object-oriented programming, where you're very careful about the object hierarchies, so that you don't need to know anything about the levels below. It's a black box. I can just program to the API. I don't need to know what's underneath the hood. That wasn't what was going on here. Shima knew exactly what was under the hood, and if he didn't like what was under the hood, he went back and said, I want this instruction to, say, scan the key, decode the keyboard for me so I can save a few bytes. And they squeezed this whole calculator, without the square root, let's forget the square root for a second, they squeezed the whole calculator into 1K bytes. So this is very different than what we do these days. Gosh, we know how big programs are nowadays. One of the things that I'm really very happy that I was able to be involved in is the release of the schematics that Tracy Mazer and I worked on. It's a great way to celebrate the 35th anniversary of such a historic product, is to make the design public, at least for non-commercial use. And so now anybody can contact Intel and get digital files of the original drawings for the 4004, the mask works, and the user's manual that they can use to, you know, write a book, teach a course, study, play with, and you know, I think that we need more of these case studies, because it's just a wonderful case study. In the field of law, the cases are all out. It's an open book, right? You can go back to the cases and see what lawyers before you, if you're a student, say. You can see what lawyers did in the past. And with computer science and electrical engineering, a lot of stuff ends up being in filing cabinets. Sometimes it gets thrown out, like the HP 9100. All those engineering drawings were thrown out when they moved to when HP Calculator Division moved to Corvallis, Oregon. Lost. We have the Computer History Museum has a 9100, but there aren't any drawings. So, you know, I will leave you now with the notion that, you know, using designs like this to help our young people learn about engineering and be inspired by engineering and go into VLSI design and electrical engineering is something that I'd like to, you know, captains of industry here, and you have some designs in your vaults, in your corporate archives that isn't part of your core business anymore, but would make, you know, just a tremendous case study. Let it out of the vault. Thank you very much.
Okay, we're going to have a few minutes where we can have audience questions now. We've got microphones up in front. If you would like to ask a question, please go to one of the 2 microphones and I'll call upon you. And please state your name and your affiliation.
Hi, my name is Dan Selix, and I worked at Intel for 17 years after these guys had left. I was wondering if you could tell us about the work that you had to do with the process engineering team at the same time you were doing all this design.
The process development was already done at Intel. So basically, I used an existing process. There was no additional work that was required. In fact, the idea of the buried contact was already basically lifted from Fairchild and used in the 1103 design. So I used that same technology that I had developed a couple of years later at Fairchild.
Karen?
I'm Karen Tucker with the Computer History Museum, and this question is for Tim. Tim, can you tell us something about the new exhibit at the Intel Museum?
Yes. So, as I mentioned, this is the core of the exhibit. It's a fully functioning replica. And then there's also an interaction area where people can see what it was like to use the calculator software and also see what was inside, how things are going on inside, to see the registers, see how the program takes through a flow chart, et cetera. And I welcome everybody to go visit this. It's officially opening on the 15th, but you can sneak preview it tomorrow if you would like.
Okay, next question over here.
Leo Brookes, Theras Systems. I have two questions. First, has anyone tried to write the 404 in Verilog and resynthesize it to see, to compare the quality of design?
I have to take exception to compare quality of design, but Fred Hittig did take the schematics and derive a Verilog simulation to do design verification on it. So yes. Does that answer your whole question?
So what was the number of transistors?
Fred, do you want to answer that? Actually, go up to the mic, Fred.
Actually, there were two different Verilog implementations that I made. One was straight from the schematics, converted at the transistor level. I found 2,304 components. I think 1,843 were FETs that were used for switching and not loads, or caps for the bootstrap loads. But more recently, I did a Verilog simulation without at the transistor level, just the RTL level, and I'd have to look to see how many gates that took. It was about 10% of an Altera Cyclone 2.8, so that makes it about 800 gates. And that includes all the memories and the ROMs.
And second question, is there a single, at least one instruction that survived, or the instruction opcode that survived until today?
Of the 4004?
Yeah.
Opcode? I don't think so.
No op.
Yeah. No, but different opcode. But a different opcode for no, perhaps.
Okay, question here.
Bob Davis, Summit Computer. One of the other big problems with the 4004 as a user and implementer was it had no interrupt.
Yeah.
Right.
And Tom Pittman did the software that was on there, the assembler.
Yeah.
Because then I used him to do the three-way 4004 system. But used it a long time ago.
Question over here.
Hi, I'm Bob Zeidman with Zeidman Consulting. So I have two questions. The first one is, I think, Dr. Fagin, I think you pointed out a section that you said was the automatic refresh circuitry for the DRAM, if I understand. Now, if I understand that correctly, if it automatically refreshed the DRAM, why was that never incorporated in standard DRAMs after that? And the second question is, I'd like to know what you think is the worst part of the 4004 architecture that you wish you had done differently.
That last question is for Ted.
Actually, I believe the first question, it was...
I will answer the second question.
I couldn't hear the second one.
Well, my career would have gone a lot smoother if I had, if the DRAMs had automatic refresh on them, because that was the biggest problem I ever had to do designing DRAMs, figuring out how to get the refresh signals in there.
Well, in the case of the DRAM, first of all, we took advantage of the fact that there was a time when we knew the DRAM was not being used, when it was fetching instructions. That's not the case in the normal non-Harvard architecture computer. So that made it more difficult to do the same kind of thing in a DRAM for regular applications. Although, I believe around 1975, another semiconductor company did file for patents on on-chip refresh of a DRAM. And in the file history, you'll find that there was a reference to the 4002. But the statements that the applicants made was they had no idea what the 4002 was. So in effect, they got the patent issued, even though the 4002 was a DRAM with on-chip refresh. I'm sorry, I missed the second.
In the architecture, which part of the architecture were you least proud of that you wish you had done differently?
Least proud of? Well, probably one is the addressing of memory. We were initially, we weren't setting out to make a truly general purpose computer. The job was to simplify the calculator architecture. And so the calculator architecture dictated a number of, there were a few things that really kind of stood out. They were talking about having displays with up to 16 digits. And we had, 4 bits for binary coded decimal arithmetic. Well, if you make it a binary machine instead of a BCD machine, 4 bits will select 1 out of 16 items. So that said, let's take a look at a binary machine. Well, if you've got a binary machine and you do add 2 binary coded decimal digits, you end up with a valid binary result, but it's not a valid binary coded decimal result. So we put in the decimal adjust accumulator instruction, and now you had a machine that could either be decimal or binary, and it could actually go between the two as needed. So that was a nice feature. The other was the lack of interrupt. We just weren't ready to put the cost of that in. We started off, and it was quite a while before we even did an estimate of how many transistors, and our first estimate was just under 2,000, somewhere around 1,900. I'm amazed that it came in as close as it did when you consider how rough our first estimates were, because, I was not an MOS designer, and as Dr. Virginia has pointed out, there weren't many people there that were MOS logic designers. They were all looking at memory circuits, and you have maybe 2 or 3 circuits, a decoder and a memory cell, and the whole circuit is made out of, those 2 elements, where you need things like flip-flops and timing and all the rest that goes into a logic circuit. So I think we were pretty lucky. We did put in the remnants of an interrupt into the 8008. And in fact, it came about one time, Stan Mazer and I were sitting around, saying, what could we do to make the 8008 interesting? And we raised the issue of interrupt. We didn't want to pay the cost on the chip, but we asked the question, what would you put on the chip to be able to add it as an afterthought? And we came up with a solution which was confusing initially. In fact, it was confusing to some of our competitors who filed for patents on the design and got it wrong because they didn't understand it. But what we decided was we could do a call instruction and force it instead of letting the processor fetch an instruction from memory. We would actually force a call to a subroutine. And then it occurred to us, if you do that, and the call will put the program counter on the stack, but unfortunately you've bumped the program counter ahead to get as it fetches the call instruction, and what you push on the stack means you've missed some of your original code. Solution, stop advancing the program counter when you recognize an interrupt. We added essentially one, you might say one gate. When you acknowledge interrupt, you don't advance the program counter, and that was the hook we put in that allowed us to add interrupt later on. There were other things we should have done because it was not easy to service an interrupt in an 8008, even with what you could do later on with it.
I want to add one thing because, as you probably know, all the chips were packaged in 16 pins. That's 16-pin packages. And we threw away about 3 times the performance by going to a 16-pin package instead of, say, 40-pin package, which in those days was also quite possible. That was not Ted's fault, actually. That was Intel's management, let's say, had a phobia about, big pin count packages. We were forced to use 16 pins when, in fact, we threw away 3 times the performance. In other words, we had 10.8 microsecond per instruction instead of, say, 3 microsecond per instruction in those days. Now, what saved us was the fact that silicon gate technology was so much faster than metal gate technology that even with that, we were competitive with metal gate chips that came out later on using four-phase designs, like the Rockwell BPS4, for example. So if I had to say what was a major flaw of the family, use a 16-pin package for the CPU.
I'd like to sort of play devil's advocate here. One of the things that we really liked about this design was that you can run this 4-bit bus through all of the chips, and it makes the PC board layout very easy. This is a very elegant chipset. When you looked at later chipsets, which required decoders and bus multiplexing logic, this is just wonderfully elegant, even at that level. Yes?
Yeah, it was elegant. It was elegant, but it was not efficient.
Okay. Can't argue with that.
Well, I beg to differ. It was necessary to get it through Intel.
Oh, of course. I agree with that.
Okay, we'll take one last question.
Hi, I'm Tom Halfhill with Microprocessor Report. I have two questions. One thing is, just for the benefit of everybody, can you give us what you can recall about the architecture, especially the programmer's model, things like how large was the instruction set, how many registers, if any? I'm assuming there was no pipeline. Just in general.
Pipeline? Excuse me?
No instruction.
Just in general, the general nature of the architecture. And then my second question is, the most common reproduced photo of the 4004, which is like on the Intel website, makes it appear that the package is made of wood. So what's that all about?
Well, let me ask the second question first. The package is made of ceramic. It may look wood to you, but it actually is ceramic package. It's a typical package in those days.
There were concerns in the early days about Silicon Gate MOS, and I believe there were, maybe you could, there were certain steps that were done to make the oxide layers smoother, a high doping of phosphorus in the glass. And the aluminum over that could be etched by phosphoric acid if moisture got in the package. There was concern whether plastic packages would be moisture resistant enough to be able to have reliable silicon gate circuitry. And so one of the reasons why the initial packages were ceramic. Later on, it was found they could deal with that.
Yeah, another thing was the power dissipation. It was 700 milliwatt, and there was a concern that 700 milliwatt was too much for plastic.
Okay, thank you all very much. If you want to talk to any of the speakers, come on forward. Thank you for joining us tonight.